right, everybody online can hear me? Let's assume that's a yes.
Yes.
All right. So for today's homework, we were looking at, oh, hold on, I don't have the big TV on. All right. Today's homework, we looked at uses of binary, octal, and decimal, and why these bases are used in our computers. We did talk about this last time at the high level, that effectively, what is the job of, well, what's the point of all this stuff we are talking about? So what is the point of any of this? Well, why do we use computers to begin with? Why do you use a computer? What does a computer do to make your life better?
Well, I don't know, my application on the computer now, so.
Okay, like okay, what kind of applications? What kind of, like what does your computer do for you on a daily basis?
I check my mail, I browse the internet, I study on my computer.
Okay.
There's a bunch of stuff when I used to work, I used to use applications on the computer to work.
Okay, so can we function today without computers? Or it would be difficult, right? Especially with a younger group, right? So, you know, I have one living grandparent, and she has an iPhone for FaceTiming with the grandkids, and well, I'm the grandkid, right? The great grandkids, they're the ones that want to FaceTime with grandma. You know, so she uses it for that one specific tool.
Yeah.
But for her, the people she interacts with on a daily basis are more experienced folk like her, who they didn't grow up with this, right? But you mentioned email, things like that, stuff that, I mean, you're getting all your announcements. You're using Zoom to attend class when you're too lazy to get up and walk to save a couple of bucks from your Uber, that kind of stuff. Okay, so we're very reliant on our computers, and computers have kind of a new, you know, the definition of a computer is much broader, right? You know, we used to think of our cell phones as phones. Now the fact that it even makes phone calls is maybe not a feature we use that often. we use it for all sorts of other things. Okay, so you know, the point of any of this is that at the end of the day, we need some mechanism for talking to a computer as a human. Understanding the low-level communication is important for a computer scientist as we invent new ways to communicate with the computer. From a consumer point of view, we care about convenient communication with the computer. Computer scientists are still consumers. Huh?
I was just gonna say that.
Yep, we're still consumers and want life to be as easy for us as possible. All right, so that being said, when we try to answer this question about binary, octal, decimal, and hexadecimal, what did we find that deviates or in addition to what we talked about last time about, you know, humans like decimal, computers like binary, base 8 can be represented fully with 3 bits, base 16 can be represented fully with 16 bits. Did we find any other rationale for why we might use these bases?
I found for the, first of all, I think as we go through them from decimal to hexadecimal, the farthest we go, so
Kushal, you're late, by the way. You missed a quiz. No, somebody just showed up late.
So, so as we go to hexadecimal, I think we're getting far from human, the easiest human communication numbering system to the easiest computer communication numbering system. What I mean is hexadecimal is easy for the computer, not for the human. The human is easier for decimal is easier for the human.
Okay.
Now, for the usage, I found that something I didn't know, that the Octal is still used in the mixed systems, Unix, Linux, or other mixed systems for the file permission. Now, I did work with file permissions in Linux before. I didn't know that.
Yep.
This
3.
yeah.
Yeah, so it's using with change mode, Chmod, the user permission, the group permission, and the everybody else permission. Yep.
So I didn't know that type of file permission is usually Octal till now. That's one of the stuff I found. Other than that, I can say that binary is the computer language. Octal and hexadecimal, just hexadecimal usages. I think we discussed that last time for color coding and for I found for in the network field they use hexadecimal and identify MAC addresses and IP addresses in version 6. So
What's a number? When we think about a number like 7, let's stay in the human world for a minute. So we'll take the number 7 as decimal. What does that mean?
it's a digit. That means that represents.
That's what it is, but what does it mean? It's a digit, yes.
It represents a number of things.
Okay, a count, a magnitude, right? So numbers represent an idea. Usually a count / magnitude / etc. whatever. But they have a meaning to us, right? We can't break things down below that, can we? If somebody says you have 7 of something, at some point we're making the assumption that the person we're talking to understands the concept of counting, of numbers. There's a baseline where you can't break that down anymore, right? So it means something. Now, in a different, let's say we lived in a weird randomized world, would it be reasonable for us to say that 7 actually means 14 things? Yeah, I mean, if we had just everything mapped like, hey, look, whatever I say, it's double, right? It's double that. So that's just because of the weird world we live in or something like that. Okay, so we can redefine through an exception, let's say, we can redefine the meaning of a number. But at the end of the day, numbers represent an idea. All right, they're delivering information about something. All right, so we typically, when we think about numbers, we want to think about things we can do with numbers, math, stuff like that. But before that, numbers also, but they have a meaning. They're a way of representing data. Okay, so regardless of the base of the number, it still has the same meaning. So 7 in decimal, 111 in binary, 7 in octal, 7 in hex. The following all mean the same thing. Make sense? Ultimately, they are delivering the same message. They just have a different footprint for the way they're delivering that message. Okay, now we know why we would use this one. This is at the computer level, zeros and ones decimal. When would we use hexadecimal? So decimal is if we are human, right? Binary, if we are a computer or talking to a computer at the lowest level. When will we use octal? You gave an example of octal, like using for the permissions of things, right? So when would we actually, can you give me, why did we choose octal for that?
Because it's distributed in three bits from hex. And from what I've read that, because currently uses the file permission as read write and execute, that always has to be read write and execute, so it's stored 3 bits when we do that action.
Okay, how many different ways are there? So talk about 3 bits. Octal for file permissions. How many different ways can you write 3 bits? Well, we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. This is 1, 2, 3, 4, 5, 6, 7, 8 different ways. Octal, right? So 8 different ways. Why didn't we just use 0 through 7 and decimal to mean the same stuff? Yeah. Why didn't we say, well, you know, if you want nobody to have permissions of a file, you'll just set its mode to 0. If you want, you know, so they all each have a different meaning, let's say. Okay, if you, you know, so you have one version of the permission, which is 0. You have another version of the position that's 1. Another version of it, it's 2. Now, really, when we think about for file permissions, here I'm saying, here's the number of unique ways we can write 3 bits. But for file permissions, what we're really talking about is read, write, and execute. And read and write and execute, write and execute, write, let's see, what am I missing? Read and execute, yep. So couldn't those numbers have represented the same thing? Couldn't we say that a 0 means no permissions, a 1 means read only, a 2 means read and write, a 3 means read, write, execute, a 4 means read and execute, a 5 means read and write, a 6 means whatever. You know, I'm going down the list. Why didn't we just say that? Could we have? Yeah, well, I mean, we invented the language, right? We're saying we're using this value to add meaning to something. And we're mapping the idea of a number, whatever that number is, to a specific permission, an idea, a read, write, execute idea on a file. Now, where this is found, and he referenced this earlier, is in Linux. There's a Chmod command, which changes the mode of a file. And typically you might say something like 755. So this is read, write, execute for the read, write, execute owner, read and execute for the group, read and execute for everyone else. These numbers are decimal, right? I'm typing at the command line, a Linux command, which was a Unix command before that, and it's expecting a human being to interface with it. So we're typing in decimal numbers, but each of these guys is an octal representation, right? Under the hood, well, we say octal because it supports 0 through 7. Those are the legal octets of the octal number system, okay? So we're going to go through and we're going to say this single number means something specifically for the owner of the file. The second number specifically means something for the group that the owner of the file is a member of. This specifically means something for everybody else who might have access to your directory wherever this file is. All right, so we can set those permissions. These have meanings. So again, we're back to this idea that a number is used to represent an idea. All right, they're not always used for math. And this is an important connection to make when we think about architecture in a computer, because more often than not, we're not actually doing math with our numbers. We're using them to represent ideas. All right, so octal, a good example here is file permissions, or any idea that can be represented in less than 8 lists. So yeah, my typing did what I said because I really emphasized that S. That's right. Can be represented in less than 8 unique ways. When would we use hexadecimal?
To define locations in memory.
Memory addresses, right? The memory addresses are the, let's call it that's the go-to move for hexadecimal. Not that you couldn't use it for something else, but we can say, or any ideas that can be represented in less than. And actually, when we say 8 here, what we're really saying here, it's not less than 8 unique ways, it's less than 256 unique ways. The largest value that we can represent, if we think about this in decimal, the largest octal value that we can represent in 3 bits, if using 3 bits, is 256 unique ideas, right? Whereas in hex, any ideas that can be represented in less than 65,000, 16-bit, 2.1 billion, 4.2 billion, 4.2 billion, this is 2 to the 32nd, 4.294 billion. Unique ways if using 4 bits. All right. So when we deal with memory, why is hex used for memory? What's a memory address?
It can be basically a MAC address.
Basically a MAC address. Well, what's a MAC address?
Every PC has a unique, every laptop and has a unique MAC address, so it's represented in hexa.
Okay, so hexadecimal might be another way of representing the MAC address of a computer, right? So you're telling me that
Yep.
a MAC address for a computer is a unique identifier for that computer across all pieces of hardware, right?
Mm-hmm.
network hardware, so you can recognize a device on a network.
Yep.
Similar to an IP address, but I don't think it really tells us what why hexadecimal is. I mean, it's a true statement to say that MAC addresses are represented in hexadecimal, but when I ask why is hexadecimal used for memory addresses, saying it's a MAC it's basically a MAC address isn't really an answer.
I think basically it's a big number, so if it would be represented in any other format, for example in binary, so it will be really large. So that's why in hexa is power to 16, so that's why it shortens the number.
Okay, so it can represent really big numbers. Why do we need big numbers with memory? Why is that important? What? Yeah, why? What problem are we solving by assigning memory addresses to places in memory? What's the actual problem we're solving?
What do you mean by problem? Like, this is the way of the computer to store and work on information. So, in the sense of a problem, I mean, what do you mean by it?
It can characterize every byte as 2 hexadecimals.
Okay, so that's something we could do with hexadecimal, but you're telling me for memory addresses. First of all, what's memory? What is it? Maybe this will be helpful to get where I want to go with this. What is memory?
The storage.
And I'm specifically here talking about RAM. All right, so it is storage. Tell me more. What kind of stuff do we store in memory? Okay. Very specifically, what things actually go into system RAM as opposed to go under the hard drive, as opposed to go into one of the hardware registers on the processor, as opposed to going into one of the cache things on the CPU? What are the things that are actually living in RAM while our computer is running? We don't want to just have this idea that these are just these ubiquitous things where, yeah, a computer has memory and that's just how memory works. Well, who made memory work? Who created memory? We did, right? We built some hardware and then we had to come up with some way of using that hardware. Now, you've told me generically that memory is used for storing things, okay? Specifically, if we're dealing with system memory, our RAM in our computer, what kinds of things do we intend to store there? Again, this is the problem human beings were trying to solve initially. Somebody built a computer, what we've defined as a computer today, all these parts that are stuck together, right? And we decided, okay, well, one of these things we put in here is memory. Well, I might ask myself, well, why? Why did I put it in there? It looked cool. Look real cool. Okay, you got all these wires and stuff like that. That is hard to understand, right? So we put memory in there because we wanted to, among other ways of storing things, we wanted to store things. What kinds of things do we store in our system memory? things that need to be relatively fast when the CPU needs to get at them. So the CPU can't hold that much memory on its own, so it needs a place to feed off, but the hard drive is too slow. So we need to strike that balance between fast enough storage and big enough storage. That's the problem we're solving, right? We have a CPU that eats instructions. We're getting ready to start talking about ARM instructions, okay? Assembly language, low-level languages have a one-to-one relationship with the CPU. Think of the CPU kind of like the game Pac-Man, all right? He's that little, abba, 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 abba. Right, that's a perfect Pac-Man rendition, right? See, you just got it, right? You should hear the way I do the ghosts too. It's too early for that. You guys couldn't handle it. So think of your CPU kind of like Pac-Man, where you feed it one instruction at a time. It's like abba, 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 and it's eating those instructions and then performing some magic trick, right? Pac-Man doesn't do that. It was probably going to be in Pac-Man 3. Was there ever a Pac-Man 2? I know there was a Miss Pac-Man. You know, Miss Pac-Man actually was from somebody recreated the original Pac-Man, and then they got sued, so they had to name it Miss Pac-Man. Yeah? Oh, old. Miss Pac-Man was just like Pac-Man, but the Pac-Man had a little bow on. Are you looking it up? Yeah, I think otherwise there might have been some other changes, but otherwise it was basically the same game. From as far as I know, it was the identical game. Okay, so the problem we're trying to solve as human beings is to strike that balance. Our CPUs are meant to be fast. That's the job of a CPU. If we jumped over there and we said, well, what problem is that trying to solve? Well, that's the guy that tricks us into thinking that all this stuff is happening really quickly on the computer, whatever that stuff we're going to use our computer for is, right? Okay, but it's supposed to do it fast. And how does it accomplish its task? What does the CPU actually do? It eats instructions, right? It takes in an instruction, says, what does this mean? Which magic trick does this map to? And then it performs that hardware circuit magic trick thing. And the hope is that those instructions that you're feeding at one line at a time ultimately accomplish a real task. CPU doesn't care, right? You hand the CPU an instruction, it does whatever you told it to do. You hand it another instruction, it does whatever that told it to do. And the human intelligence behind that ultimately, hopefully, delivers a solution to some other problem that we rely on computers to do, right? And that CPU, it's hungry, right? It wants to keep eating those instructions fast. And we can only store so much stuff on the CPU with its hardware registers and stuff like that. We can maybe load the next instruction in there, something like that. You know, as our CPUs have evolved, we kind of created more of a pipeline type situation where it's like, you know, let's kind of get them buffered up there a little bit so we can feed even a little bit quicker. All right. But if we're going back to the very early days and we abstract this, we say CPU is going to eat really fast. If he's feeding directly off the hard drive, which is relatively slow, that CPU is going to be a bottleneck, right? Okay, he's ready to stuff his face. See, the hard drive's not going to give it to him fast enough. Okay, so the job of memory, the problem we were solving with memory, is we said with our system RAM is the specific what I'm talking about here with memory. That's the thing. It's like 8 gigabytes, 16 gigabytes, and your computer 32, whatever. All right. The problem we're solving with that is we are striking that balance. It's got to be fast enough to be noticeably better when the CPU starts feeding off of it, yet it needs to be big enough to hold enough instructions that we have meaningful programs on our computer, right? Otherwise, if it was just super, super fast, but it was really tiny, we wouldn't have programs that can do anything, right? They would be too simplistic, or we'd have to come up with another hack and say, well, we'll load, we already do this to a certain extent, but we'll load only a very small percentage of the program into the super fast memory. And then we'll keep the rest in the hard drive and just hope for the best that the stuff that's important is already loaded in there, right? And then try to keep up on the back end. All right, we see real life examples of this kind of stuff, right? You know, where you have kind of people who have an assembly line, maybe you're helping some folks move. You get a whole bunch of college students together, right? And they're all handing boxes off to each other, and you maybe have two people at the end who are actually loading onto a truck, something like that. So you try to buffer it up so there's enough stuff for the people who are loading it on the truck. But then when you start getting the heavier stuff, that pipeline slows down, right? So all of a sudden the people by the truck are sitting there waiting because they have no boxes to feed off of because it was loading from the hard drive into memory slower. Make sense? So we have real life examples of almost all of these problems. Again, human beings are the one who came up with these solutions. Make sense? We solve all of our problems in terms of the tools we have in front of us. And that's our own mind, that's our own experiences. So often, certainly, and definitely the first stab at a lot of these problems looks very human, right? And only once we kind of get more imaginative or kind of forced into, you see that idea of think outside the box, right? Do you have to kind of say, well, I have limitations as a human what I could do, but does this computer let me break the rules a little bit? Can I do something that really wouldn't make sense for a human, but kind of works in a computer, or at least happens fast enough where works well enough, something like that. All right, so the problem we're trying to solve with memory is we're trying to strike that balance, have enough system memory to have programs that are big enough that they do stuff, they're meaningful to us, word processors, video games, whatever, okay? So we need to have enough memory to hold programs that have enough instructions that presumably programs with more instructions or more complex programs that allow us to accomplish more things. There's some truth in there at some level, right? But it also needs to be fast enough for the CPU to eat quickly, as quickly as possible, whatever that compromise is. All right, that makes sense? All right, so that's what memory is. That's the problem we're trying to solve with memory in general. Why is hex used for memory? Why do they have it in this one? So you told me it can represent really big numbers. Well, why do we need big numbers for memory? In the context of what we just talked about. Okay, larger data. Tell me more about that. I'm not necessarily fishing for a very specific answer. Just tell me more. And we'll kind of take us down a path. Okay. I think at the end of the day, computers always store binary. Yeah, but go back to what we said earlier. All these numbers mean the same thing. Okay, but you said, well, computers store stuff as hexadecimal, but they don't. They store it as binary, zeros and ones. If you were to go and look at memory, we peek under the hood at our system memory, dive in there, right? This movie is going to be before, I think, all of your time, but you should watch it. It's called Lawnmower Man. The movie Lawnmower Man. Which is actually a funny name for it, but anyways, he gets embedded into this artificial, and he becomes the artificial intelligence in this computer, and in the movie, he's inside the computer. Okay, so if you were to crawl inside of a computer, you were flying along inside of memory, what would you see? You'd see a whole bunch of zeros and ones. That's what memory holds, is zeros and ones. Okay, so now we're back to the question about hex. So why is hex used for memory? Why is, so we're going to pivot off this top number. This top thing I think is the most important thought here. It can represent, where, you just got to move, but where is he? Galib is supposed to wave his hands every 30 seconds. Is he even online? Is he on the computer? Or check?
Yes,
Where are you?
I'm at home.
Yeah.
It's too cold outside.
Yeah, you know, these lights just went off.
Oh,
We almost had a major emergency here.
I missed my job.
I saw the fear in Waleed's eyes too. He was not a fan of the dark, right?
No, no, I don't care. So it's fine by me.
I don't know. Hey, you don't got to get all defensive about it. I get it. Oh, so you said we had enough light. So it's kind of like a night light. Okay, fair enough. All right. So, you know, I like this first statement here that hex, one of the, again, operating off this idea that numbers have meaning, right? And a hexadecimal value, especially if we think about it in terms of 4 bits, can hold big numbers. Why are big numbers beneficial to us when we're dealing with memory?
Okay, since you're not fishing for a specific answer here, first of all, I would like to, on the first sentence, I can say that it can be used to represent, to simplify big numbers, of binary, I can say that. And I can route, the idea that you're saying that, hex can be used to, show the numbers, simplify the numbers, the idea I mentioned before. This is not from memory, by the way. The idea I mentioned before for ID address number 46, in which hex is used to shorten the binary representation of the address, to shorten the number of bits that are shown.
Okay,
I
so
think it could be the same for the memory. It shortens the not the number, it shortens the representation of the.
good comparison with IP version 6. You have a misunderstanding of what the goal of IP version 6 is. New slide. You just grew a new slide. Okay, yeah, it's kind of what he said. Does hex for memory solve a similar problem to hex in IP version 6? Not a networking course, but hey, you brought it up, dude. So, what is the goal of IPv6? Why do we need it?
And I'm.
Hi, you brought it up.
I'm there like 40%. I can say that basic stuff. It was it was there to replace IP version 4. It uses 120 bits per, so it can be allocated. It can have much more addresses than the IP version 6. It uses hex representation for the same reason I thought I was saying just because, and then you don't need to put it on that it shortens number of bits represented by
No, you're making some good sense. In fact, you're saying everything that's right except your conclusion. You're drawing the wrong conclusion off the right logic. Why do we need, so you mentioned IPv6. Let's talk about that, and then we'll roll it back to memory. It's the same answer. All right. So with IP version 6, you said it can hold more unique addresses. than IP version 4. Why do we need to hold more unique addresses than IP version 4?
Well, because we have many more users of the dive more into networking.
Not really. Just give me the high level.
Because yes, we
Yeah, lots of machines on the network. Each have to have a unique identifier. Right? All right. So is it fair to say that there was a risk of us running out of addresses? Okay. And part of that, the more the networking discussion is how our address is handed out, and they would give a university like this a big block and we would only use 20% of it. So we'd have wasted addresses, stuff like that. Not important for us in here, but the idea is that we have more computers that want to have unique identifiers on the internet than IPv4 could uniquely represent. Again, numbers are used to mean something, to represent something. So with IP version 4, where we had 3-bit addresses, right? So you could have 255, 250, so you had 256 times 256 times 256 times 256. So 256 to the 4th power. So 4.3 billion unique addresses. Big number, but they decided, you know what? We might have more than 4.3 billion computers all on the network at once. Now we alleviate some of that with local area networks and stuff like that. But if we just pretend like the whole world is on one gigantic network, there's probably more than 4.3 billion devices that are on the internet or on a network of some kind, right? Okay, that's a problem. So what are we going to do? Well, we're going to switch it over. We're going to do 4 2 to the 4th power. What am I doing here? No, it's 65,536 to the 4th power. That's the number of unique addresses we can have with IP version 6. More. Right? Doesn't matter how much more, it's more. And now we can have more computers on there. All right, so let's go back to this slide. What problem are we solving by using hexadecimal to address places in memory? See, we're connecting the dots to something she said earlier. We're close. Okay. So I mean, I want you to feel like upset that you're getting so many wrong answers, but this is how learning takes place, right? Okay. We're so close. We just need to connect that final loop.
Store more information using less space.
All right. I don't like the last part of it. What do you mean by store more information?
I mean, it uses how I should say, large binary numbers in fewer digits.
Okay. No, that's kind of what she said earlier. Now we're back to what is memory. I've kind of referenced probably a couple times in here a previous day that memory is kind of like a city, plots of land, right? You know, that but memory is all one big long street, and all the stuff. You know, if I want to go to house number 8, I go to bucket 8. If I want to go to house 2 billion, I go down the street a long ways. I don't need to have these complex addresses like we have in real life. We have a street number, a street name, a city, blah, 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 all this stuff, right? Okay, everything's one big long street, which seems simple. All right, so with that in mind, what is the advantage of big numbers in hexadecimal?
As you said, it's for the IPv6, you use to help with the big numbers and storing in memory.
Help with the big numbers and storing in memory. Let's try to say that way better. I'm not convinced yet. Taking that concept that I said, we have this big long street, okay? And I've referenced that you have house number 0, house number 1, house number 2. How big are those houses? They're all the same. That's an important piece here. For memory, they're all the same. Depending on your memory manager, might they be 2 bytes big, or they could be 4 bytes big, or they could be 8 bytes big, right? We can decide how big we want to allow our houses, each house to be, but they're all the same size because that's how memory managers, more of an operating systems concept. They're all the same size, but that hexadecimal value, because if we're talking about 2 bytes, well, 1 byte, 2 bytes, 4 bytes, these aren't giant numbers, right? 4 bytes is 32 zeros and ones. We don't need hex to represent 32 zeros and ones, right? We can say, well, hex lets you hold it in a little bit smaller footprint, which is kind of what we've been, where you've been pushing in that direction.
Right.
But ultimately, computers store zeros and ones. Human beings like those numbers that look a little friendlier. Not that hex is that much friendlier, but ultimately, a computer needs to store it in zeros and ones, right? That's how it's actually stored, is zeros and ones. So if you want 4 bytes, you got 32 zeros and ones on that plot of land. You go next door, you got 32 more zeros and ones. You go next door, you got 32 more zeros and ones. Why do we need hex? What's the advantage of hex for for addressing memory? Yep. No, not about making it easier. Anybody online want to help them out?
I think it solves the problem of converting into binary. Hexadecimal eases us to convert into binary. That's the reason we need.
Here, I'll give you a global hint. It's not about making life easier for humans. We haven't chosen to use hexadecimal to make life easier for humans. So here, let me ask it a little bit different. Why is 32-bit hex used for memory? And 32-bit can be written as 4 hextet. Sextet, hextet. Hex used for memory.
I'm still going to run back to the IPv6 example you mentioned, not mine, and saying that
To display error messages.
Say that again?
Error messages.
Oh, error messages? Nope.
Use hex to represent more. I'm trying to amend the sentence I said earlier into a better format, so represent more. We can we can store more in memory by using hex.
Okay, I think we're pretty close there. So the bigger the value we use to number or represent the buckets of memory, the more unique elements store in memory, right? So if we think about our memory as one big long street, and we just assign, whatever our file system is, we assign a certain size of each house on that street. Hexadecimal allows us to, in a smaller footprint, represent more houses. That makes sense? So if we use a 32-bit addressing space, So that's 2 to the 32nd power, which is 4.294 billion unique plots of land in memory. Now, if we say that each of those plots of land can hold 4 bytes, I'm just giving a house size. Let's say we're using a memory manager that gives us 4 bytes. So if we say something like, if we use a memory manager, that chooses to store up to 4 bytes at each location in memory, and we use 32-bit to represent our number of locations, we probably represent those 32 bits in hex. So they visually, well, so they have a smaller footprint. What is the maximum size of RAM we can have on this computer using that using those rules? So that would be the number of unique addresses is that times 4 bytes. Make sure is that number. This is the number of bytes. Which is equal to, so divided by 1024, that's kilobytes, divided by 1024, that's megabytes, divided by 1024, that's gigabytes. Is equal to 16 gigabytes. So if those decisions are made, if we decide, you know what, the amount of memory that I have this physical thing of memory, and that memory does have physical buckets associated with it, okay? But then we do have a limitation of the number of physical buckets that we can physically have. But let's just say that that's not a limitation. Limitation is how we count, okay? So we decide, you know what, I'm going to use 32 bits, 32-bit values to label each of those buckets. This is bucket 0, this is bucket 1, this is bucket, 2,000,000,007 down the street. And the operating system says, I'm gonna let you store 4 bytes in each of those buckets. Probably more than that, because we certainly have computers that can hold more than 16 gigabytes of memory. But if these are the rules, this math works, right? So if we say that the operating system lets us store 4 bytes at each place in memory, and we have 2.1 billion places in memory, 2.294 billion places in memory, I do all that math, that means I can store a total of 16 gigabytes of stuff in memory across 4.294 unique buckets of memory. I might have wasted space in some of those, right? If I can store 4 bytes in bucket number 3, and I only put 1 byte in there, I have 3 bytes of what's called internal fragmentation. So I didn't quite get my full 16 gigabytes of full capacity there, because I'm being a little wasteful, but the hope is we have enough memory that this isn't a big deal. All right, but from our perspective in here, the punchline is we use hexadecimal to represent the number of things on our street, because we have the manufacturing capability of creating these large memory sticks that have lots of physical buckets on them. And we need to have a way of maximizing the number of those physical buckets that we can talk about. You don't want to run into a situation where, and representing it in hex has the advantage when they're talking about the memory address. It's this big long thing. I think comes out to about 48 bits is what modern, I think the current version of Linux that Ubuntu 64-bit Linux uses 48-bit addresses. So 2 to the 48th is the unique number of buckets of memory. And then if we presume that each bucket holds 4 bytes, that's kilobytes, that's megabytes, that's gigabytes. So that is, well, 1,024 terabytes of memory would be the maximum addressable memory using 48-bit addresses. So 48-bit addresses that we might represent in hexadecimal for visual purposes. So rather than having 40, if we were to show that memory address, you might have 48 zeros and ones, and a human being would look at that and say, looks unique enough, right? Or we can have, what did I say? So 48 divided by 4. Nope. 12 unique 0 through 9, A through Fs to represent that same value. They both have the same meaning, right? We don't get any benefit of representing it one way or another. Just here's our way of describing it to you. But at the end of the day, wave. All right. Galib gets 2 zeros for the day so far. It is just not good. All right. So,
network.
all right. So the idea is that the more bits we use to represent our memory address in the operating system, the more unique places in memory we have. And then the operating system can say how much they want to store in those places, which is probably going to be limited by, you know, how the hardware is built. You know, you can't say, well, I'm going to store 700 bits in each memory location because that lets me have even more memory if the physical memory only will hold 64 bits at an individual bucket, something like that. All right, so what we're doing here is we're marrying the physical to the software. Okay, the operating system to the physical hardware. But bottom line is that the amount of memory we have is represented by a number that tells us the number of unique things we can store in memory. The operating system, along with an agreement it makes with the hardware, dictates how much we can store at each of those unique places. All right, make some sense? All right, so we go back to our picture back here. That's not the picture I'm looking for. This is the picture I'm looking for. Okay, so our motherboard here has a CPU plugged into it and all this other crap. All right, and our CPU is feeding off the buffet that lives in memory. And then there's some inner workings here that do some pipelining and stuff like that. But this guy gives us stuff faster than this guy does. Still faster than this guy, still faster than this guy. We can say that this guy's pretty fast, but still way slower than this guy. Make sense? If we're color coding this right, we probably want to make that green, right? Okay. So makes sense? The purpose of memory, that's the job memory is solving, sitting there in the middle. Okay, so why is hex used for memory? To store more unique things in memory. up to the limits imposed by the physical hardware. Okay, so now, next concept is Big Endian versus Little Endian. This has to do with how do we store values in memory. Okay, so Big Endian is an order in which the big end, so that means the most significant value in a number, is stored first at the lowest storage address. Little Endian is an order in which the little end, the least significant value in the sequence, is stored first. For example, in Big Endian computers, the 2 bytes required for a hexadecimal number, or 16 bits, requires 2 bytes. A byte is 8 bits. 8 plus 8 is 16. So we need 2 bytes. Can be represented. So number 4F52 would be stored as 4F52 in storage. If 4F is stored at storage address 1000, for example, 52 would be stored at address 1001. That's if we use Big Endian. All right, so this is the number, and the lowest address is where the most significant is. In Little Endian, if we stored that same number, the 52 would be in the least significant, would be in the lower memory address. It's the least significant value of this number, but it's stored, so you can think of our numbers being stored in reverse in Little Endian. It stores the least significant digits followed by the most significant digits in contiguous memory. Now, that may or may not have a benefit when you're doing certain kinds of math operations, and you certainly would have the ability to flip them because you're dealing with 2 physical unique memory locations. But these are 2 different ways that we can take stuff and put it into memory when we're storing it. So now we're taking it one step further, right? We've talked about hexadecimal numbers in terms of the number of unique things we can address in memory. And then we've talked about that the total amount of memory we have is a negotiation between the operating system's counting system, how many bits it's going to use to represent. Realistically, I don't actually know the answer to this, but I mentioned in Linux, it's using 48-bit memory addresses right now. I showed you a few minutes ago, 2 to the 48th gives you that many unique places in memory. My guess is, so that we're not being wasteful of our hardware, that probably is greater than, probably by a pretty significant margin, than what's coming out of our most bleeding edge hardware manufacturers in terms of the number of physical elements, physical buckets that can hold stuff in a memory chip. So even though we're capable of addressing 48 bits of unique memory space, we probably don't need the full 48 bits to do it. So some of those addresses, some of those 2 to the 48th unique addresses would never be used because we can't, the street's not that long. Make sense? So this gives us some growing room. It's like when you buy clothes for a 2-year-old, you know, and in 3 weeks they're going to be bigger. So you let them grow into the clothes type thing. All right, so we picked a bigger value, 48 bits, so that we can easily deal with the current hardware and we can grow into more hardware until it becomes a problem. Then we'd probably bump it to 64 bits, something like that. Okay, so this is how do we, when we put stuff into memory. So before we talked about the number of unique places of memory, and each of those places is a place where we put stuff. And the stuff we put there, we can store in a couple of different ways. We can store it in the most significant digits first or the least significant digits first. chances are it might be stored in hexadecimal. So we'd actually say the most significant hextets first versus the least significant hextets first. But at the end of the day, it's actually stored in binary zeros and ones. All of those things, though, have the same meaning, right? The number 7 in decimal means the same thing as the number 7 in binary, means the same thing as the number of 7 in octal, means the same thing as the number of 7 in hexadecimal. 7 is 7 is 7. Is the same meaning. How we represent it when we're working with our assembly language, okay? Which, you know, and I realize that that's where a lot of our answers were coming from, right? Is the idea that human beings maybe don't like hexadecimal. We prefer decimal, and we're going to choose to work with decimal as often as we can. We're relatively more okay with working with octal or hexadecimal than directly with binary. Not so much that we hate zeros and ones, but because zeros and ones, we're going to be more error prone with zeros and ones, right? We can probably roll with getting 4 zeros and ones correctly represented in a single hextet, a single base 16 value, 0 through 9, A through F. We could probably pull that off relatively error-free, or at least have a fighting chance. But if you ask me to write down 16 zeros and ones, if I'm copying, somebody gives you you know, 2 bytes, and you have to copy 16 zeros and ones, there's a legit chance you flip one of those bits. Make sense? All right, so all this does have to do with how are human beings interfacing with the computer through the tool that we use to talk directly to the computer, which is assembly language. All right, so let's get that. But why? Humans need to talk to the hardware one way or another. The hardware works the way it works, and we need mechanisms to tell it what to do. We create layers that live between the human and the hardware. The more layers, likely the more convenient life is for the human, but the less, well, but the more overhead that exists in the translation from, let's say, human to binary, because ultimately the computer is going to work in binary. When do we write it in binary by hand versus when do we take advantage of our power tools? So human beings prefer to write high-level code, which then goes through a compiler, which then turns into bytecode, which is effectively assembly code, which then gets loaded onto the CPU and translated into, well, actually, it then gets assembled, turning it into, each line of code translates to a one-to-one relationship with the CPU. So it's going to take your line of code like this, which we'll talk about, and it's going to turn that into a bunch of zeros and ones for whatever this command is. So the move command is one of the magic tricks the CPU knows how to do. And let's just say it's magic trick number 4. Okay, so you're going to have a binary representation of the number 4. Maybe it's in 5 bits, you know, depending on the number of instructions you want to see your architecture supports. So if it's 5 bits, that means it can support 2 to the 5th power of unique instructions. So if we say that this particular architecture only has 32 instructions, then we can say, we can represent that in 5 bits. But you need more unique instructions than that? Well, we can use 6 bits. Now we can have 64 unique instructions. 7 bits, we can have 128. 8 bits, we can have 256, so on and so forth. We represent things with numbers. And a number, whether it's written in binary or decimal or hexadecimal, has a value. Ultimately, CPUs are going to feed off binary because that's what computers work off of. But that first binary number, so we're going to feed the CPU a string of binary values. Maybe the first 5 bits in my little example here is the instruction we're asking the CPU to do. Okay, let's just say we have 16 bits. That means I have 11 bits left to work with. Okay, maybe the next 3 bits are the operator, something like that. So, so in this case, you're going to represent this guy in 5 bits, maybe this guy in 3 bits, this guy in 3 bits. So you actually only are going to use 11 total bits out of your 16. So you would just have zeros in areas that weren't being used. Make sense? And then when the CPU actually goes to process it, it's going to go in here and say, what do you want me to do? Magic trick number 4. No problem. Magic trick number 4 needs 2 parameters. I'm going to send in these bits. I'm going to send in these bits. That's what it means to be hooked up to magic trick number 4. Does that make sense? So at the end of the day, when it actually runs on the CPU, it's running in binary. Okay? Now, as a human being, we might prefer to write it in the high-level code. Then we might prefer to have it compiled and assembled, whatever. But we are capable of talking to our computer in a low-level language, which is what we're looking at right here. This is an example ARM assembly program, all right, that shows some stuff. How do humans solve problems? We use our memory, we ask questions, and repetition. If you had a class with me before, you will almost always hear me use this example, okay? And we'll connect Dr. Locklear in with this. It's the grand ideas of computer science. They're all intertwined, all right? So human beings solve problems, memory, repetition, and asking questions. Then I usually have a slide called the mapping. Memory is done through variables. Asking questions is done through conditionals. Repetition is done typically through loops, functions, etc. Okay? Then we'll close that loop by saying, pun intended, programming languages. All programming languages have facilities for those or for these 3 things. All of them, 100% of them, all. 100% of programming languages have facilities for these 3 things. If it doesn't, it's not a programming language. Okay? It doesn't matter if it's high level, low level, machine code. It has these facilities. Make sense? Now, just real quick, and we're going to look at we're going to kind of start on this slide next time. So I'm going to put a little note here that says start here. I'm just going to give a quick glimpse at this just to give you an idea. Okay, so we are comparing two things. This is asking a question. We are going to one place if the value we're looking at is less than the other value. So if R0 is less than R1, we're going to jump to LB max, which is just a label. So this is the if else, right? So if this is true, jump to another place, which is here. If it's not true, then keep going. We'll move into R2, the value of R1, or R0 rather. Then we will branch to L rest. This is the rest of your code, skipping the contents of what was in the if. All right, so this doesn't look like a high level if statement to us, but it is. If this is true, do this stuff, then move on. If this is false, do this, then move on past this. So this is the body of that if. Does that make sense? So even our low-level languages, which are just representations of our high-level languages, have facilities for all those things. All right, so next class, we're going to start looking at ARM assembly in more detail. We'll probably actually write some ARM assembly next class. So we'll be, I think I might, just because this is only an 8-week class, I might use an online, like web-based assembler rather than us installing something, just so we can kind of experiment with it quickly. Like, hey, here's the URL, let's type it in and just start doing stuff. But there are assemblers for like Linux and stuff like that that I might use or at least mention, whatever. All right, no homework for Wednesday, but you'll probably have an assignment Wednesday for over the weekend. So I will see everybody Wednesday morning.
Thank you.
Yep, have a good one.
Thank you, sir.
Thank you.
I have a question, and I'll talk a quick relative question.
Sure.
You mentioned throughout the class that you mentioned pipelining in the talk. And so when we were the second research, I think when we were looking at processors, multi-processors, stuff like that, almost all that I looked at use pipelining, and you mentioned that it's relatively a new thing.
Well, it's something we keep improving on,
Oh,
typically by throwing more cache memory. So pipelining is effectively the idea of let's buffer up some stuff so we're ready to deal with it more quickly. The more faster memory we get next to the CPU, the more we can technically pipeline, right? So it's certainly something that we keep improving upon by adding more memory or bigger memory. The bigger the memory, the more we can pipeline. Because ideally, the more stuff that the CPU is about to eat that we can move out of system memory and into one of the caches, the better, because caches are faster than system memory. Yeah, so it's not a new thing in that we just started pipelining, but it's something we continually improve upon with each new architecture.
That's not what I meant. I meant, was there a time that we did not have the pipelining?
Oh, yeah, I mean, yeah, in the early processors. Yeah, the first processors would have just fed directly off of the memory.
I just thought it was a default thing with processor creation.
Yeah, well, I mean, but at what point is it still pipelining? Maybe it is pipelining to say, I feed off of this one connection, this one pipeline to system memory. So if that's the case, then pipelining existed from day one, right? But then it just kept getting better by improving the speed of memory. Once we ran out of that and our manufacturing got better, putting more memory that used to be super expensive, putting it on the processor, so on and so forth. Somewhere in there, we're playing that balance game between cost of the processors so that people can afford them, that kind of stuff. That's why when you go and look at some of the server processors like Xeon chips, a lot of times they're, you'll be 3-4 times as expensive, but when you look at the difference is in like the L1, L2 cache, the amount that can be supported for that pipelining, so that the processor can eat more quickly, even if its clock speed is the same. We removed some of the slowdown in Pac-Man coming back to get his next bite. Make sense?
Yeah.
Okay.